Okay, welcome to another lecture in GR. We have started introducing more structure into the space-time manifold, and the structure that we have is that one that arises if you do the following experiment. You take some piece of matter that has a direction. Technologically, that would, for example, be a gyroscope, and then take that directed thing as a vector, move it to another place in space or in space-time, and then see what the resulting vector will be. The resulting vector will be a new vector in a different tangent space. And so what we wrote formally is that we have a map that we called tau that generally depends on gamma, and I hope I convinced you with the example of the surface of the Earth. Remember the globe that I had, that it really depends on the curve gamma, so that's not an overkill to include that into the map, not only on the start and on the end point, as one may think naively. So you take something from the tangent space at the point t of the curve, so the curve t and u are curve parameters, and map it to the point at u of the curve. I'm not sure I had this type of picture that I usually draw, so let me draw one. We have a point here and a curve gamma through the manifold, and so the point gamma t could be here and the point gamma u here. And we are now really relating points in different tangent spaces. So I could have this, let's say, green tangent space here with a vector pointing in some direction, and then I end up with a vector in another tangent space, which is maybe here, that vector. So that blue one would be, or maybe I just indicate it like that. Here, that's the blue part, and the orange part was the initial, the green part was the initial tangent space. Okay, so that's the picture you should have in mind. And as I said, this is not a structure that comes out of what we already defined before. So a differentiable manifold a priori doesn't have this structure. This is really something we impose. This is new data that comes from physics. Now I told you that we can define this for vectors, first of all. So, I mean, this definition is really for vectors, for vector fields, because these are the spaces in which vectors live, but we can easily extend that to tensors. And for that, we just apply some general rules. And the rules are the following. So the idea is essentially the rules allow you to say how an arbitrary tensor transforms or is mapped under this connection mapping if you already know how a vector is mapped. And so the first part of the rule just says, actually it talks about an even simpler object than vectors, namely scalars or 0-0 tensors. So let's take a 0-0 tensor. A 0-0 tensor is just a real number. Let me call it C, or maybe let me take R. I think I used R in the past for real number, so it's a real number. And the point is, if this real number is mapped, it is not changed. So that's just for R equal to R. And of course, as I said, that corresponds to the case of a 0-0 tensor. So in other words, a 0-0 tensor is transported under this map just by keeping it constant. So that somehow makes sense, because I want to capture with the whole thing, what does it mean that something remains the same? And for a vector, this was not trivial because it's mapping to different spaces, but a scalar is not depending on a tangent space, that just stays constant. Now, the second part of the rule asks what happens, or answers the question, what happens if you have the tensor product of two tensors? And if you already know how the tensors transform individually, then the answer is the two should just transform by applying the transformation rule to the individual tensors individually. So I just do this. I apply it to T and apply it to S, and then I take this tensor product. So we could also say the tensor product commutes with the transport map tau. And then finally, we have something that we have already seen similarly for Lie derivatives or for flows, that we have seen that the flow commutes with the trace, and the same is true for this transport map. It commutes with the trace. Okay, and the claim is now, and we will see more about this claim also in the exercises in the case of the derivatives, which we will just introduce in a few minutes, that this really allows you to derive the transformation rules for arbitrary tensors. But let me just do it for illustration for a 0, 1 tensor. So that we haven't seen, because a 0, 1 tensor is, of course, generally is a very different object than the 1, 0 tensor. A 0, 1 tensor is essentially a covector or a covector field in this case. So, when I now talk about vectors and vector fields, you should always understand it. Of course, it's defined on the whole manifold as a vector field, but sometimes I'm just referring to the vector at a particular point. And here, indeed, we took a vector here and mapped it to here. But of course, I can then define this everywhere on the manifold, this map tau. I just need to put the curve that goes through the desired point, and therefore I can transform a whole vector field. So everything I say here naturally generalizes then to whole fields, despite the fact that we define it pointwise. So let's take such a 0, 1 tensor, and I just call it again omega, because it's essentially a covector. So how do we understand how a covector transforms? One idea is to just apply to a vector. And now you have probably, already noticed that if I apply a covector to a vector, we get just a number. And we now know how a number transforms, namely nothing changes, as said before. So we can say this is just equivalent to the transformation applied to omega and v. But now I can write this differently, and I will now not write this out again explicitly, but I hope you remember from last time that if I have this wv, I can write it as the trace of the w tensor and the v tensor. So in other words, this is really equal to the trace of a tensor product, and therefore I can apply these two rules. And this essentially means they just both transform individually. So this trace rule and the rule 2 applied to this particular case tells me just transform it by applying in tau to ut. Of course, it's always a tau gamma ut to the omega. And then I get a new covector and apply this new covector also to the transformed vector v. And that's the same. So that's essentially rule 2 and 3 applied. Now, the question was, how does actually a covector transform? Now, to get this out of what I wrote, I make a small replacement. I take what is here in the bracket and just call it vector w. So I can, of course, now also express w in terms of v. How do I do it? It's just the inverse transform. I can express v in terms of w. And the way to do that would just be to say, this means that v is equal to the inverse of this tau map, but the inverse is just obtained by changing the order of the arguments t and u applied to w. Okay, now we have everything in place. I can now just insert this expression for v here into that expression, essentially, or more precisely, actually, I do it here in this one. And what I get is the following. So what I conclude from this is to say, what I really want to know is how does the omega transform under tau gamma. So that's the question. What is this object? Now I understand this object if I know how it acts on a W, but that is something I already know because that's now exactly this line. So I know this is just equal to that thing here and therefore equal to that. So this is equal to W applied to V, but omega applied to V, but V is now just tau gamma T, U, W. Okay, maybe to summarize, the conclusion is we now know how a tau acts on such an omega, on a 0,1 tensor. It acts by saying just apply the omega to the transformed vector, to the back transformed vector. So that's the inverse transformation here. Okay, and then similarly you can extend that once you know how things work for vectors and covectors, then obviously general tensors can always be built as linear combinations out of them. And so you really get the transformation rules or the rules for all these objects. Okay, that was essentially something to complete what we started. So remember the definition of that map was given already in the last lecture. And I will use certain properties of that definition again, and I will remind you of them as we proceed. But we now come to a new chapter which introduces a concept which is again a kind of derivative, namely the covariant derivative. And I will at several places point out the differences to the Lie derivative that we already learned. So the covariant derivative and the Lie derivative are really different things. They're different notions of how to kind of capture the notion that something changes, that a vector changes. We call in the Lie derivative, it was kind of, the question was, if you have a flow, how does a vector field that we observe while floating on that flow, how does this change? Now we don't have a flow, but we have this transport map tau. And in a vague sense or in a rough sense, this tau will take essentially or do the job of the flow that we had before. But there will be some differences, and we will, let's say, at the end of this lecture, certainly understand these differences. So let me immediately, yes?
There's just a small question about the definition of the affine connection.
Yes, please.
Just about the order of the arguments. So the question is there any good reason for the order of the arguments, like that it's first
T
the
and U, of U and T.
Yes.
I guess that. Yes. Okay. I think it's yeah. I mean the map or starts from T and goes to U, and maybe the idea why the T is written to the right and not to the left is maybe the following: if you do the composition. So if you ask yourself, what happens if you have this map UT and now you compose it with another map? The way in mathematics we usually compose maps is by reading them from right to left. So if I say this is the first map, and now I apply a second map, then I write it to the left of this. So let me make here some space therefore. So if I now compose it with another map, let's say tau from U to V. So that's the second one. Then this is equal to tau of V and T. This is all for the same curve gamma. And now you see it somehow makes sense because you read these things from right to left. The composition here connects this U with this U, so to speak. So that's just, you could see it as being notationally consistent with the usual notion of writing composition of maps from right to left. Therefore, we write the arguments from right to left. I hope that answers the question.
Yes, that's great.
Okay, so let me then immediately proceed to the definition. And this is, of course, a very important concept, by the way, this covariant derivative. As you will see, this is really the notion of the derivative that will replace the usual derivative that you learn from flat space and flat space-time in the formulation of equations, of physics equations. So for example, if you ask later, and we will look at that, how do Maxwell's equations look like in curved space-time? And of course, you know, in Maxwell's equations, there are derivatives there. You take the derivatives of the electromagnetic field. Of course, you already probably know in space-time, this is a field tensor, but you take a derivative. And this derivative is usually just expressed as a partial derivative, because in usual flat space-time, we just think of a kind of well-behaved coordinate system in which everything kind of behaves, or I mean, the coordinates are, for example, orthogonal and rectilinear, and therefore you really get the right expressions. Now in GR we work with space-time, and in addition we work with coordinates, with arbitrary coordinates. You may have curved coordinates, and in these curved coordinates a derivative may no longer look like a partial derivative in the usual sense. So if you just take the partial derivative with respect to a coordinate, that's not something that is independent at the end of the coordinate system. You would not get physical laws that are independent of the coordinate system. You would get chart-dependent physical laws. And I explained at the beginning of the course that physics is really, on my sketches, usually on the left-hand side, and on the side where we have the manifold and not on the chart. So we want the chart-independent notion of a derivative, and the covariant derivative is exactly such a thing. So that's the reason why it enters physical laws, because the physical laws will not be chart-dependent. So you should really think as this is the right way to think about the derivative if you're not in flat space-time, and also if you're not using rectilinear coordinates. Okay, that's why this notion is so important. So let T be a RS tensor field, and V be a vector field. Okay. Now, this is, of course, the input to the derivative. We have a direction given by V, and we have the actual object we want to derive. And we call the derived object nabla Vt. So that's the covariant derivative of T in the direction of V. So that's also something you should notice, like a partial derivative in what I said before in Euclidean geometry. A partial derivative is, of course, depending on a direction and in the direction of these coordinates. And here in this generalization, a covariant derivative has this direction given by a vector. And so what is it? It is, again, a vector field, namely a vector field of the same type, an RS, or sorry, a tensor field of the same type. If it was a vector that you take the derivative of, it's still a vector, of course. Now I need to say how this new vector field is defined. And this definition that I'll now write down will very much remind you of the definition we have seen for the Lie derivative. And I will do it pointwise explicitly here. I didn't do that for the Lie derivative, but actually for the Lie derivative, you should also think of this being pointwise defined in order for this limes to be well defined. So what does it do? It takes the tensor at a curve gamma. This curve gamma will be a curve defined along the direction V. So you walk the curve up to parameter t and then take the vector back to the point that you're interested in, namely the point P, and compare it with the tensor there and divide everything by t. So let me first finish writing the definition, and then I hope things will become clearer. Like in the case of the Lie derivative, there's a simpler way to write it. I could just write it actually as a derivative of this expression here, evaluated at t equals 0. And now let me also write down what I already said in words. Gamma is a curve, and is seen I've here made a choice. I've here put the 0, and this is reflected by the fact that I choose the curve parameterization such that at parameter value 0, the curve passes the point P. And of course, that's important. The velocity vector of the curve at that point 0 should be v, the direction of the derivative. Okay, that's the definition. Now let's see how, whether again we can understand this definition. So remember my arrow that I always use. So that's, let's suppose now the t is this arrow, not the v. But let's suppose the v is the direction in which I walk. So I walk towards you, let's say. Now I start with this arrow, that's the t, and the derivative as I walk to you. So the derivative in direction v of this is now not defined just for one arrow. Let's suppose I have now an arrow field. So I have here an arrow and I have one here. And now the question is, okay, unfortunately I only have found one such arrow, but let's take a replacement. So let's take this other pen here. So that's the second arrow. Now I can ask myself, and of course there will be infinitely many arrows. It's a whole field. At every point in space, there's an arrow. Now the question is, if I take this second one, the pen arrow, which is not at point P, but at point gamma t, it's on the way as I walk a little bit forward. I take this point and with a gyroscope transport it back to where I am, to P. And now the question is, what's the difference between this back transported pen, this arrow, and the field value, the arrow I had originally here? So again, this is something that really not only depends on this arrow. There were two arrows to start with, so I transport this back and compare it. And if it changes, then this derivative will be positive, namely in the direction of, or will be non-zero in the direction of how this thing changed. So for example, if we are now in flat space-time, if this is the arrow here and the other arrow points a little bit upwards, I transport it back, the derivative will essentially be this difference between the arrows. Of course, this is all infinitesimal, so there's a change and I divide by t, but that's the usual notion you are probably used from derivatives. Okay, so in other words, the physical meaning is if you compare things to how they would, you compare a field of arrows to how the arrows would be oriented if you would just transport a gyroscope. So a gyroscope, if you equip space-time or my path with the arrows generated by a gyroscope. So I take the gyroscope, transport it, put an arrow here in the direction of the gyroscope and so on. Then the derivative of that field is zero because there is no deviation from the gyroscope because the whole field was defined by the gyroscope. Okay, I hope this notion is clear. I will certainly be happy to say more about this because this is probably a main or crucial point to get the intuition of what's going on in the whole thing, that you have this understanding of what a covariant derivative means in this sense. So please feel free to interrupt me here or later if you have questions about this notion in particular.
Yeah, so there are two questions in the chat.
Yes.
Which may be interesting to everybody. So the first question is that this person noticed or asked if it's correct that if you want to do electromagnetism, for example, in flat space, but for example in spherical coordinates, there you already would use the covariant derivative.
Yes, that's absolutely correct. So that's a point I will stress again later, maybe when we come to a further discussion of the derivative. But the summary of that discussion that we will have today will be that you only have the usual meaning of the normal partial derivative if you are in flat space-time and you use Cartesian coordinates. So if you use polar coordinates, that's already no longer the case, and you have to use that derivative. That's correct, yes.
Mm-hmm. And then there's a second question. This person noticed a similarity to a notion encountered in QFT. So just the covariant derivative, I guess, in non-abelian gauge theories.
Mm-hmm.
I noticed, so he asks if there's any connection to this notion. And also, he noticed that also in the definition in QFT, they also use something that they call a connection.
Yes. So this is certainly connected, but here I would prefer not to go into an explanation, because we would then require more material, actually, this QFT. But maybe I can later, in a more, let's say, private question session, go into that. But that would require some time. And it would also probably require me to first think a bit about how to present it. But I will be happy to answer that later, maybe after one of the lectures. But I guess this would go too far within the lecture.
And there's also a small remark in your definition. I guess the limit should be going to 0.
Oh yes, I think this is the same mistake I made last time. Thank you for noticing this. This should go here to 0. Yes, that's right. Yes, you see, I did too much of this stuff that we do at the end, where time, we usually look at the far infinite future, and we will often see such limits, but at the moment we are not there. So thanks for noticing that. So these were the questions you mentioned. Oh, okay. Then let me make a few notes about the definition. The first is that one that we also made in the case of the Lie derivative. So here is clearly a similarity. This thing is indeed a vector field. I mean, this is already part of the definition, a tensor field. But keep in mind, whenever I define something, I need to make sure that the definition is well defined. And the definition, of course, here contains a claim. Namely, the claim is here, is this tensor field defined by this? Why is it really a tensor field? The reason is the same as in the case of the Lie derivative. I take here a tensor, I apply a linear map that brings it back to a tensor which is indeed living in the same space as this one. So this would be, I couldn't subtract this from this, but I bring this tensor back into the tangent space TPM, so I can subtract the two, and you know the subtraction, like the addition of two tensors, is of course again a tensor, the division as well, because the division is something like an addition, and a multiplication, which is also, of course, part of the tensor space. And there was a very excellent question last time, am I allowed to take the limits? And now I stressed we should really think of this pointwise. I also will introduce a footnote in the Lie derivative case. It's also true there. And if we think pointwise, then we are in a vector space where we can use the usual limit rules that we know of. So there is no problem there in this case. And because we actually assumed, by the way, that the whole remember, so the reason why I can say, okay, once we are in the vector space, we can do the usual rules. The maybe more detailed reason is that you should think of this in a chart. Of course, this is a chart-dependent definition, but remember the differentiable structure of a manifold was defined by saying that there exists an atlas whose chart transition functions are all differentiable. So I cannot talk about the differentiability just without talking about charts. And you should think in the same way here. If I have something like limits or even a differential, then go to a chart and check whether it's differentiable there, because there we understand what differentiability means. And clearly in a chart, this is just essentially a tensor that consists of components. It has for example, a vector field has d components, and we understand differentiability there. And this is the right notion of differentiability, because by definition, it's the differentiability induced on the manifold. So in other words, the explanation why this differential is defined is because it's defined on a chart where these are just this is just an RD, a tuple of real numbers. Okay, so we have convinced ourselves that this is indeed a tensor. Now another note, and this is actually some note I will also come back to, and this is a main difference also to the Lie derivative. Namely, if I now take the covariant derivative and evaluate it at one point, then the claim is this does not, this is again a tensor, but this new tensor does not depend on values of v at any point different from p. So what do I mean by that? So if you look at this definition again, then the v was actually used, actually maybe I should put here something that I didn't. So I do it pointwise, and at any point, and put this in orange, the vector will define the curve. So this curve gamma that I've defined here is just defined by saying it should exactly have this direction v at the point p. And to define this thing at the point p, I only need that curve. It's irrelevant what the other directions are. So only the vp enters the definition. Hence, it's obvious that any other, as long as I'm only interested at the point p, I don't need to know what the vector field is at other places. And this is not true for the Lie derivative. In the Lie derivative, we couldn't say that the Lie derivative along a flow defined by a vector field v only depends at the point p on the flow in this, on the direction of the vector at this, or on the vector at this point p. And why this is not the case, I will explain again. It's actually one way to see it is to look at coordinates. And what I will therefore do is now to write down the coordinate expressions for the covariant derivative and then compare it to the coordinate expression of the Lie derivative. And then this difference that I just noted now will again be visible in these coordinate writing in the coordinate form. So just have to bear with me for a moment, and you will understand why this note would not be correct for a Lie derivative. Okay, so as I said, to do that, I want to understand, or at least write down the coordinate representation. So what do I mean by the coordinate representation? So first of all, what I want to do is to say, if it takes, okay, I could do it in the general case. This would be quite cumbersome and not give more insights than if you just do it for a vector field. So we do it just for 1, 0 tensor fields. So instead of t, I write again w. So this is now this a 1, 0 tensor. And now I'm interested in the coordinate I of this new vector field, or vector at the point P. Let's evaluate it at the point P and ask ourselves, if I take an arbitrary vector W or a vector field W, take the covariant derivative along the direction V, what's the I component of the resulting vector at point P? So let's just evaluate that. And to evaluate that, of course, I need to just insert the definition. Now I will, because I'm interested in the components, I will write the definition in terms of components. And maybe you remember from last time that this map tau gamma has components that are usually indicated with I and j, w, j. So this expression here is essentially just apply the map tau to w. So this corresponds, if you look at the definition here, just to essentially this. Oops. So it corresponds to this thing here, just written in components. T is now W, of course. So W, I should also say where W is evaluated at gamma T. And okay, just here needs. And the whole thing has to be evaluated at T equals 0. So that was just the definition of the covariant derivative, and now I looked at the components. So what I need to do, and for that I need more space, I will write the equality here. I will have to evaluate explicitly the derivative to T, to the parameter T. And here I have again a product rule because I have a factor here that depends on T. These are really now numbers. So that's a very normal product rule for numbers because these are the coefficients. So that's just a real number or a function of T if you want. And that's another function of T. But for every T, this is a real number. So what do I get when I take the derivative? Let me first apply the derivative to the second factor. So I just leave the first factor unharmed and evaluate it at T equals 0. But what happens if I evaluate this at T equals 0? By definition of the transport map, if I transport something from 0 to 0, it's just the identity. And the identity in components is just the delta function. So I can write this tau gamma as delta. And as I said, I will still have to take the derivative of the second part. The second part is just this wj gamma of t, evaluated at t equals 0. And then we have the other component. Now I need to also, of course, take the derivative of this tau gamma of 0t. And so this one is now really evaluated at separately. So, I mean, I only now apply the derivative to this part. That's why I put these brackets around it. So space is still a bit tight here. So let me put this on a new line. So I have this, and then the second factor this time will not be derived. So I just keep it gamma and evaluate it at the point 0. So that's the derivative. And now I can just write this a bit in a neater form. So first of all, the delta function, of course, goes away. And I think we still have to do some work. So here, this is a derivative of a curve. So this is the derivative of a function along a curve. But we know that the derivative of a function along the curve is the same as the velocity function of the curve applied to the function. So let me write this here. So this is the same by definition as taking the velocity function, velocity vector of the curve at the point where I'm interested, gamma 0, and apply this to the function wj. And then, of course, we take the yes, that's what it is. So let me just copy that down and apply the delta function, and also use the fact that this velocity, by the definition we've just made, must coincide with v. That's what is written here. So instead of writing the velocity, I can just write v. And so what let me write this maybe here as a reminder. What I do is that, of course, v is itself vk d to the dxk. That's just a decomposition I can make. Now, taking everything together, I have this v applied to the rest. So I have vk, and then this partial derivative applied to wj. But instead of writing the partial derivative, I can write here a comma k. I think I already introduced that notation earlier. So that's the first term. Now for the second term, now we have to remember something from the last lecture, namely one of the basic properties of that thing. And maybe let me add here something, namely that this has to be evaluated at t equals 0. If you look at the definition of the parallel transport of this thing, of the tau map, then by definition, this whole object here is equal to these gamma symbols that we introduced times the velocity vector. So what this thing is, I'll also write this here below. So this bracket here is equal to gamma I j k, and then times the velocity v k. So to see that, just look up the definition of the taus that we've made. So there, this is just explicitly stated. Here I've now written this in with the v. At that time it was, I think, just gamma dot k that we wrote. But v and gamma dot k are the same thing because the curve is exactly along v. So I can therefore write here gamma I j k, and then we still have the double uj, and of course this vk that I just had. So I put this all together, and everything here has to be evaluated at the point P. So these are all coefficient functions. So each object here that appears in this expression is itself a function that takes a value at every point in the manifold. For example, this is the function, what's the kth component of the vector at every point, in particular at point P, and these coefficients are themselves functions that are defined at any point of the manifold. Okay, so that's our expression. That's the coordinate expression of the derivative. Now you see, the derivative really deviates from the usual partial derivative that you do in analysis in flat space-time, because the partial derivative in the direction of a vector v would just be this term here. So that's what you would write if I tell you how does w, the vector w, how does the jth component of the vector w change as you move along the vector v? That would be the answer. But here we see that the covariant derivative is different. Oh, I just noticed an error here. I've forgotten to apply this delta here. So this j should be transformed into I, of course. So it's the i's component. This is just by applying the delta function that I had before. But you see here, there's a second term. And this second term depends on this parallel transport that we introduced on the tau map. So because a space is not flat, or just maybe because we choose strange coordinates for w, there will be this additional term here. And from now on, you will see that all the physically motivated derivatives we will have to take into account that term, because, as I said before, they are covariant derivatives. Let me make, before the break, one more remark. Namely, what we can do is just to look at the special case. We can ask ourselves, what happens if I look at the i's component of the covariant derivative along the vector field that is defined by d to the dxk of the vector field d to the dxj. So I just take the vector fields defined by the coordinates. And of course, that's now very easy to see from this expression. So here I have arbitrary vectors. Of course, if I take the vector field just along the coordinate, I only have an index that corresponds to the corresponding j, for example, here. So I can just read it off from this expression. So in particular, the coefficients are constant. So the derivatives of a coefficient, I mean, there is no coefficient here, or the coefficient is 1 if you want. So this is just constant. We only get that term with w and v equal to 1, essentially, for the corresponding index. So what you can read off from this is just the gamma symbol. So it's that. So this gives you another interpretation of these coefficients that we introduced. And what is the interpretation? The interpretation is each of these coefficients corresponds to the following thing. Take a vector in that points in the j coordinate direction. So for example, if this is my j coordinate, or this is the direction I get by increasing the j coordinate, but leaving all the other coordinates invariant, and I take this vector in this direction, and now I take essentially I look how it changes as I move in the k direction of my coordinates. For example, this could be the forward direction. Then there will generally be a change. So generally the moved vector will kind of maybe no longer be aligned with the coordinates. And now this dxi extracts the i's coordinate of how the vector changed. So to summarize, I take a vector in j, transport it along k, and look at what's the i's component of the change. And that's what these symbols tell me. So these symbols really tell me now for any possible direction how things behave as I move in an arbitrary direction and look at the change in an arbitrary direction. That's why I have 3 indices. Okay, now we have this important expression or these important symbols introduced. These are symbols, I think I mentioned that already last time, we will encounter them very often. So these are things you should really get familiar with. So remember this definition as well. I will at a few places today say you should remember things. One of them last time was already the coordinate transformation of these things. Of course, from this expression I could again derive how these transform under changes of coordinates. And I will say a few more things about them after the break. But let's first make a break until 1 o'clock. And as usual, I stay here during the break, and I'm happy to take questions. Jan, are there any questions in the chat?
I have a question.
Okay, yes, please.
So you said that the covariant derivative does not depend on any vector other than Vp. But
at the point P, yes.
Yeah, at the point P, but the definition uses the curve gamma of T, which is the integral curve of V, which depends on the vectors around P. So how is the definition independent then of the vector?
So that's a very good question. So the argument I gave so far was maybe not entirely complete, because actually it's your question should, it's an excellent question, but there's even a more drastic way you could have asked. You could ask, is this thing that I wrote down here actually well defined? In the following sense, someone could say, the only condition I impose on the curve gamma is that the curve gamma should go along this vector V. And there are, of course, many curves gamma that satisfy these two properties. And now in principle, it could happen that for these different curves, I get here a different value, even at this point P. So it could even be that it's worse than not only depending on Vp, it could be that it's not even well defined, that this whole definition depends on the different gammas. And we will now, we have now derived a coordinate expression of this. And this essentially gives you a very rigorous answer to exactly that question, because the coordinate expression that we have now tells you what are really exactly the things you need to know to get this value. And of course, in this coordinates expression, we just use the definition. So from this derivation we just did, so by writing it in coordinates, we can now read off. Obviously, it depends really on the components of the vector v. It also depends on the components of w, but also on the derivatives of w. But for example, it doesn't depend on any derivatives of v. So it's really only v that enters. And so essentially the rigorous answer to your question I can give you is this expression here. So first of all, this expression tells you it's well defined. So there was no unknown thing that depends on other things of gamma. So for example, it could be that the curvature of gamma, the second derivative of gamma, would enter. This is not the case. So there's no, this suffices. And in particular, also no derivative of v enters. And this object here, the only object of V that enters here, is just evaluated at the point P. So that's the maybe better justification of what I said here. Here, this is true. What I said here is true if once we have already, let's say, established that this is well defined. Because if this is well defined and the condition is only that, then it cannot depend on anything else. Does this answer your question?
Yeah, that makes sense. Thank you.
Jan, is there anything else that I should discuss or answer?
No, there are no questions in the chat.
There are no other questions. Okay. Maybe actually during, I think it was during the break last time or so, someone asked about whether these objects here, d to the dx, are actually forming a basis of the space of Tm, of the tangent bundle. And I said, no, this is not the case. And I referred to a theorem. And at that time, I only knew the German name of the theorem, namely the Satz vom Igel. And I now looked up what the, I somehow forgot the English name, but the English name is just the hairy ball theorem. Maybe it's also sometimes called the hedgehog theorem, but I think it's really the hairy ball theorem. And this theorem tells you that, for example, if you have a sphere, you cannot comb it. You cannot comb a whole sphere, and that's maybe the abstraction of the hedgehog, in such a way that you never have a part where the hair kind of separate in two directions. And this is the reason, so this is one example, the sphere, which shows that such a vector field cannot be a basis of the full space. Because if you want to take or define this as a vector field, or if this was a basis of the sphere, of the tangent spaces of the sphere, of Tm, the tangent bundle, these vectors, because they are coordinate, they are derived from coordinates, are always non-zero. But this hairy ball theorem tells you if you want to fill the ball with hair or with such vectors, at some point there has to be at least one zero vector. So that's what it means mathematically. But this vector is not allowed to be zero because otherwise the coordinate would not be well defined. And that shows that these vectors here don't fall, or these vector fields don't form a basis of the tangent bundle. This is only true globally. Locally, I can always do it. So locally, I can just cut out an open region, a chart, and within that chart, this forms a well-defined basis of the manifold restricted, of the tangent bundle restricted to that chart. So this just as a little addition to the question, which was a very good question that was asked last time. Maybe if people are around, I may also ask a question to you. We have noticed in the TA meeting that, or discussed that the attendance in the tutorial classes is pretty low. And this could now have at least two reasons. One reason could be that you're just attending them later or look or watch the recordings. The other reason could also be that you simply don't have time for them or don't actually do the exercises. And I would be interested if anyone has comments on that or an opinion of what we could do to maybe improve in a way, improve the service to you, in the sense that making it maybe more accessible. Maybe it's just a matter of, maybe it's just an organizational problem that some people cannot attend because it's an overlap with other courses. I'm aware that in this lecture there are people, for example, from Basel, and it could well be that these exercise classes are not well coordinated with them, or at least the online one, and that these people watch the recording. So if there's anything that you think we may change to make it possible for you to attend the exercises, that would be useful for us to know. So you can either tell me now or also write me or to one of the TAs an email with your comments about that. Also, if there are other reasons, if you, for example, think the exercises are too difficult or too simple or don't actually help you understand the material, all feedback is, of course, very much appreciated, in particular during these times where I don't see people, and usually we have these occasional talks after the lecture where people provide actually quite important information about stuff they observed during the lecture that could be improved or changed. So it's even more important now that you give me some feedback, and also to the TAs. Maybe connected to that, I should really encourage you also to try at least to do these exercises, because the course is really such that in the lecture I mostly treat things on a rather abstract level. I introduce definitions, like now for these gamma symbols. But now if you want to understand what are these gamma symbols really in a concrete example, so let's take the sphere. And now the sphere, I told you, the sphere is an interesting curved manifold. So I used it in several examples, and we could now ask, if I take usual coordinates like spherical coordinates on the sphere, what are then these symbols? Are these something you already know? And so this is something you could do in the exercises. We will, for example, in a week from now, we will try to have exercises with such concrete examples. And so this is really necessary, I think, to understand what's going on, to also see the examples. And these are not part of the lectures. That's the division of lecture and exercises, that the examples are mostly in the exercises. But they're still, you should regard them as an integral part of what you should learn to understand this topic. So this is just a little bit of encouragement. And I hope that you can really at least look into the exercises and maybe solve part of them, even if you don't have time to do everything. So maybe just out of curiosity, and I hope people are back, let me make this small, let's say, poll of who among you is actually watching just the recordings of the tutorial, because that would at least give us some hint that at least the recordings are useful. I mean, probably this mostly applies to people who also just watch the recordings of the lecture, but among those who are here, if you watch the recording of the tutorial rather than the online one, if you may press yes now, that would give me at least hopefully a rough estimate of whether this is useful. And otherwise press no. Otherwise, I don't know who is actually taking part of this. Okay, there are a few people, okay, still on the single digit level. I see 6 have pressed yes, or 7 have pressed yes, and 10 no. Okay, thanks anyway for this small feedback. And again, for those who are not here in the break, I said those who have feedback about the organization, the timing of lectures, whether they should be online or not, please send us a message if you have any particular, let's say, suggestion of what we could change to improve the availability of these things for you.
Renato?
Yes?
There was a comment actually in the chat that maybe you want to comment on. So this person said that it would also have been possible to go the other way around, starting from the metric tensor and then defining the connection automatically, and then defining power transport. But maybe you want to say
yes.
Also
okay. Yes. Yeah, this is a very good point, and I will also come to that one in more detail. But for those who already know about metrics on manifold, we haven't introduced that concept, but it's indeed a possible approach, which we will actually understand in detail, is that you can first define a metric before we define this transport that I've introduced now, and then the metric induces a transport operation on the manifold. And that's a possible way to get the transport, and then also the covariant derivative from there. However, I've chosen another path, which is kind of the more general thing, because a parallel transport is defined even on manifolds that don't have a metric. And generally my let's say philosophy for this course is that we introduce concepts in such a way that we understand what do they correspond to in physics. And I told you now a lot about these experiments with gyroscopes, and this is really to make the point that the notion of covariant derivative can already be understood from these experiments with the gyroscopes that I mentioned. And as I said, I will later maybe come back, or certainly come back to this question, but this is a choice I made. And we will also understand the other possible choice later. So we will also see how from a metric we get all these notions. And we will not have to redo the work. We will just to put the missing connecting element to see what a metric defined on a manifold has to do with this transport that I just defined. Okay, so I hope it's okay if I don't further comment on that, but I will definitely come back to that in actually quite a lot of detail. Okay, so after this break, let me say a few more things about the covariant derivative. One thing that is also worth a note is the following. If I take the covariant derivative in the direction of a vector that I scale with a real number r. So let's again take our example of the tensor field being a 1,0 tensor field. Therefore, I just write W here. And I now take the derivative with respect to RV instead of only V for an arbitrary real number R. And we know that, I mean, that's obvious from the definition. You also see it, by the way, from this coordinate expression. If you like, if you scale up the vector V, this just results in an overall factor. So what we get is just R times delta or nabla V omega. And this is also, so R is a real number, and this is therefore also called R linearity. So we say that the covariant derivative is R linear in this argument, in this direction argument. But actually we can say more. Let me say that. So what we can also do is to say, let's evaluate the derivative at the point P. And now what I actually just noted again in the break, answering a question, is that this whole thing depends on Vp and not on other points. I said that, or maybe I think I wrote this already before. Depends only on Vp. I mean, of course, it also depends on W, but it doesn't depend on other parts of the vector field. And there was actually a question in the break about that, and you can really verify this claim from this expression here. So this is the coordinate expression of the covariant derivative, and you see that it only depends on v evaluated at the point P, but not on a derivative of v. If a derivative of v would enter, to evaluate the derivative of v, I would of course need to know v at different points, but I don't here. So this claim is also true. This thing evaluated at P only depends on P. Because of this, I can do the following. Let now f be any arbitrary function on the manifold. So C infinity n. And now, instead of just scaling the vector v with a real number r, I could scale it with a vector. This gives a new vector field, namely the vector field f times v. So the vector v, the vector field v, is scaled at any point on the manifold with a different number. And the number is given by f at that point. Okay, now I do that. So I apply this again to w, and I evaluate it at p. But because of what I just said, that this only depends on the vector field at the point P, I could as well replace here the scaling by f of P. So instead of scaling the vectors differently at every point, I scale all the vectors V exactly with how they were scaled or have to be scaled at the point P. And because the whole expression only depends on what happens at the point P, this doesn't change anything in the result. So I can write this. But now I can use the R linearity. So this we already established, because f of p is by definition always the same. It's already evaluated, so I don't change the point now. So I can therefore write that this is equal to f of p and then the derivative to v of w, and that's the whole thing evaluated at p. But this now, of course, means, so because this whole thing is true for every, or okay, maybe I write one further expression. Now I can again say I just multiply the whole result again with first with the vector field and evaluate at the end at the point P. So now I have an expression, namely this one is equal to this at any point P. So I have actually established that this thing here is really equal to f times bw. And this means that it's not only R linear, but it's C infinity M linear. So that's what C infinity M linearity means of this argument, of this thing here. So, okay, that sounds now like an unimportant remark, but it is actually very important because it also goes in the other direction. So if, and that's only shown in the lecture notes, I will not show it here, but just tell you, and if you want to look at the proof, you go to the lecture notes. If I have some expression that is C infinity linear, then this means that it's actually pointwise only depending on the value of this argument at that point. We will see that later in a concrete example if that wasn't clear, but essentially my claim is here we showed that because the covariant derivative is such that it only depends at each point on the vector at that point and not on the whole field, it is C infinity linear. But we could have shown the opposite. We could have assumed it's C infinity linear, and then we could have shown, therefore the covariant derivative has to only depend on the point P at every point, where on the vector field at the point where I evaluate it. Now, I mentioned several times that this is not true for the Lie derivative, and let me therefore remind you now more precisely what that means. So compared to the Lie derivative, for the Lie derivative, we have some time ago, I mean, not so long ago, but maybe last week, actually also evaluated the coordinate expression. And the coordinate expression, I just write it down again, but we did that, so you can find it in one of the earlier notes of the lecture, looked like this. Now you should compare this expression that I just wrote down with the expression that we have here on the right-hand side. Maybe I'll mark it, something more visible here. Okay, maybe I need to go up to mark it. So we had, I think, yes, this was the expression. Let me here mark it so that we see it also on the right-hand side. And now you should compare this to that expression here. Then what you will see is that the first part of the expression, the first term, is actually exactly the same. So, in other words, if you take the Lie derivative or the covariant derivative, in both cases we have a term that has these partial derivatives of the component of the vector that we derive. But then there is a second term, and in the case of the covariant derivative, this second term now depends on this additional structure that we imposed, which tells us what does it mean to transport something in parallelly. So this transport map tau is somehow is characterized by these gamma symbols, and it still also depends on the vector, but not on the derivative, whereas the Lie derivative has no such additional structure, there is no gamma ijk. However, it depends on the derivatives of the v. And therefore, if I want to know what is the Lie derivative at a certain point, and you just give me the value of the vector field v at the point P, then I'm not able to evaluate this derivative, because the derivative depends on the whole neighborhood. It depends on how the vector field changes, and I could not evaluate this. So that's one of the major differences. So to link this again to physics, in the Lie derivative, we had this picture of the river on which I float with a boat, and I look how a vector field on the sky that I look at lying on the boat changes. Here it was important that the river was not just one vector, so I didn't only know the direction of the boat, I had kind of the whole river with its turbulences. So for example, if the boat would turn while I'm floating, that's a consequence of the fact that the vector field, if I go a little bit to the right, is maybe, or the river is flowing a bit faster on the right than on the left. So it really depends on how the vector field or the flow of the river changes in the neighborhood, because that certainly has an impact on whether my boat turns or not. So in a way, this thing is really reflecting the fact that these directions are encoded in the flow. Here in the covariant derivative, we have no such thing. This covariant derivative is defined by me just saying in which direction I walk. I have no river that tells me whether I would now turn and so on if I float somewhere. I walk in a certain direction, but the gamma tells me how directions, if I would have a gyroscope, what it would mean to not change. This gives me kind of a reference. And so we really have a kind of different notion also physically. So here the reference was the river, and here it's the gyroscope that just says, okay, what does it mean that things don't move, or that things stay parallel? Okay, there's a lot of discussion about the differences between them. There's of course this physics difference I just pointed out, and there will of course also be a mathematical difference, and one of these mathematical differences was the one I just pointed out right now. Now, this was the expression for the covariant derivative of a vector. Now I will not do the calculation for a covector, because all these calculations are quite similar, and they are given in the lecture notes. But I can, of course, still, I should state the result. So we could look at the 0, 1 tensor, W, and here the covariant derivative of the 0, 1 tensor omega would be given at the point P by, now it looks very much again like this thing here. So compare now to that. This is again the covariant derivative. So you shouldn't look at the Lie derivative now. I'm now back with the covariant derivative. So the first thing just depends on the partial derivative of the components of omega j k. Of course, it's now a covector, so the components are downstairs indices. And then I also have this gamma symbol. So the gamma I j k. Here's a minus sign. So that's one of the differences. If I transform a covector, I get this minus sign. This is just what the calculation shows. So I haven't showed you the calculation, but you see that easily. And then that's the expression. So you see the similarity to this thing here. So, I mean, apart from the minus sign, of course, there has to be a different index you sum over. Here you sum over the upstairs index of gamma with the downstairs here in order, I mean, that has to be the case. Otherwise, the summation convention wouldn't be correct, as you remember probably. And this can be generalized. So for maybe, okay, again, I will not now write it down for an RS tensor, but let me do it as an example for a 1, 1 tensor. That's already containing all the structure you need. So what happens if I take the derivative in, let's now say in direction k. So now I simplify things a bit. Here I always had this arbitrary vector. But of course, if you understand how it goes in one direction, we know everything. We just need to take that and sum over the different components. So let's look at the covariant derivative of a tensor, of a 1, 1 tensor field and the components ij. So again, what we have, the first expression or the first term in the sum will just be the partial derivative. So that's the thing you would certainly expect to have. You have this partial derivative, but then we have these gamma correction terms, and the one is the first one for the index. So for each index, if you want, this is just a way to memorize things. For each index, we get a gamma symbol. So the first gamma symbol is for the up index, so it has an I up, and then a summation over something, so I call the summation index R, and the K is always the last. This is in which direction I go. So this K here corresponds to this K here. Then I have the T Rj. So this is a 1, 1 tensor. It has two indices. And then it has also a covector part, a lower stair index. Here I have a gamma symbol entering like this, and then TIS. So that's the rule, and probably can now easily see how it generalizes to higher order tensors. Again, this is not something that I now calculated, but it's easy to do the calculation once you have this for covectors and for vectors, because it's essentially just a tensor product rule that can apply, and the exercises will give you more insight on that. Now there's a piece of notation I want to introduce, which I will use very often. So this is not only a side remark. I will write this often as Tij semicolon k. So because this appears so often, this whole thing, that we take the covariant derivative of a tensor and then evaluate it with respect to a basis, we just have this new symbol. I should, however, warn you that this symbol is highly misleading. Why is it highly misleading? It suggests from the order that you take the Tij component and then take the derivative of that. But this is not what it's saying. If you look at this, it's actually the other way around. You first take the case derivative or the covariant derivative of T and then look at the components of this. And this is really a very different thing, because here the derivative acts on the 1, 1 tensor. And then, of course, you can look at components of the tensor. Whereas if you would understand it as this is an object, this is actually just a function, because it's now the components. And if you take a derivative of a function, there will be no gamma symbols and so on being involved. So that would be equal then in that wrong understanding to the comma notation. So remember this, that this really corresponds to that. And if you then want to evaluate it, you have to remember this expression. So that's now one of these things I mentioned before you should really try to remember. It looks complicated, but once you have seen the pattern in it, it's actually quite easy to remember. I mean, you probably see it already now that there is a nice pattern. It's not that you have to use up too much memory capacity to memorize this thing. Okay, now this, another maybe remark connected to that. If I can define a new tensor, let's call it S because I've already used T. And this new, so remember a tensor takes as input covectors. So for example, a phi and vectors, for example, a V and a W. And I define this as the covariant derivative in the direction of V of a 1-1 tensor T. So T is still our 1-1 tensor, and this evaluated at phi and W. So this is again a note. And my claim is this is again a tensor. So what is this, does this claim mean? I already told you that the covariant derivative of a tensor is again a tensor. But here I'm saying more, because the covariant derivative is kind of the thing that I mentioned. So before I made the claim, let me just write it in a different color here. Earlier I made the claim that this thing is again a tensor. But what I'm saying here is that if I even look at the direction itself as an argument to the tensor, then I get a higher rank tensor. So remember, a tensor is essentially an object that eats vectors and covectors. And here I'm just looking at the tensor where the V is already put in. So this only, if T was a 1-1 tensor, only eats one vector and one covector. Here I define a new tensor, namely a 1-2 tensor. And this tensor eats one vector more, namely the direction itself. So this is therefore a higher rank tensor, and the claim is this is still a tensor. Now, of course, it's a one with, again, if T was 1-1, this will be a 1-2 tensor. And okay, this claim is not completely obvious, but from what we have done, we can immediately see that it must be true. So why do I say it's not obvious? If I said the same thing about the Lie derivative, it would be a wrong statement. So I could just have replaced here in this expression that I just wrote here, this thing with an L for Lie derivative. So maybe I just write this down so that you remember. Whereas, just that you have to, let's say S bar, I could have defined this thing. Lie derivative of Vt Vw is not a tensor. So now, what do you think is the reason for that? The reason is something that we have already discussed before, and it's probably the reason also why I emphasize this point so much. I told you right before, if you look here on the right-hand side, that the covariant derivative is C infinity linear in this first argument, in this V, and that this is not the case for the Lie derivative. And indeed, that's actually the reason for these two statements, simply for the reason that if you look at the definition of a tensor, and at that point I just mentioned this as, okay, this is just definition and accepted, but now you see the relevance. In the definition of the tensor, a tensor is an object that takes these things and has to be C infinity linear in each of its arguments. So the reason why this is not a tensor is simply because this object is not C infinity linear in V, but only R linear in V. Or now to say it in different words, this object here depends, if I evaluate it at the point P, not only on V at the point P, but at other points, and therefore it's not a tensor. So the C infinity linearity that we used when defining tensor was really the property that makes sure that if I evaluate the tensor at the point, then it only depends on the inputs at that point. That's an important property of the tensor. And that's actually why you can really think of a tensor field as a field of tensors. Because if you go back to the definition, and if there wasn't this C infinity linearity, then it could be that a tensor field, or that a tensor field cannot be interpreted as a field where at any point of the manifold you have a tensor. So it's really this C infinity linearity that makes this true, for the reason I mentioned before when I did this little calculation before the break. So I hope remember that I did this thing with the F, or after the break, I don't remember. So there was this little calculation where I showed if this function, if the tensor is independent of F, or if it can be multiplied with F, then it's really only depending on point P, and that this holds in both directions. So the thing to remember is the infinity linearity of an object means the object depends only on the input at that point if I evaluate it. That's the bottom line of this. And this is now luckily true for the covariant derivative, and this is a very useful property of that object.
There is a question
Yes.
in the chat. Maybe can you read the chat somehow?
Yes, I can try.
To explain this in words.
Okay, so the last one.
Yes.
Aha, okay, yes, I think this is a good point. So, okay, I think there is a distinct, okay, so the question is about the following. We have not yet looked at properties, but you will actually in the exercise series see properties of the derivative. And the derivative, as you will see, will have the usual properties that derivatives have. Namely, for example, the following. If you take the derivative of something like f times the tensor, then what you get is a product rule. So it's like taking the derivative of f and then the tensor plus f times the derivative of the tensor. So in other words, this, if I look at this nabla here and say this is an object that eats a tensor, then this object is not C infinity linear. So that's what this thing here says. So what I mentioned before is only C infinity linearity in the argument here in V. And that argument here is the argument where you feed in T. This is again not the same as the arguments here of phi and W. These are the arguments that are fed into T. So the question was essentially, isn't that thing here somehow contradict? I mean, if I understood the question correctly, and otherwise you have to maybe complain, but if I understood it correctly, the question is, doesn't this fact, which is a correct fact that you will see also in the exercises, contradict the claim that the covariant derivative is C infinity linear? And so to be clear, the answer is this nabla thing is C infinity linear in this argument V, but it's not C infinity linear in this argument here. I hope that clarifies it. Okay, so okay, for those to whom this comment wasn't clear, it will probably be after you did the exercises. Now we have actually, I think, yes, seen a lot about tensors. Let me just write down this rule here again for the case of a vector, just for illustration reasons. So, of course, in the case of a vector, now if I write it down with this semicolon notation, it looks like this. And now you see already the pattern. First, just write it with a comma, which means it's the normal partial derivative. But then for each index that the object had, and of course in the case of a vector, we only have an upstairs index, write the gamma symbol, and then take as the second lower index the direction in which the derivative goes, and sum over the first lower index with the given object that you want to derive. So that's the thing. There's now something I want to say about transformation rules. So I insisted in the first part of the course a lot on the fact that the objects that live in the manifold are defined independently of any coordinate system. Here, of course, I have a coordinate-depending expression because these are all things that are only defined with respect to coordinates. These are the components with respect to a basis. Now, what I told you before is that this object here are really the components of a tensor, which, I mean, this follows from the fact that I just told you here more generally that if we define such an object here, that's again a tensor. And so therefore, these are the components of a tensor. So in particular, we verified that even this direction thing, the V part, can be understood as, or this argument can be understood as the input to a tensor. However, if you now look at the individual terms on the right-hand side, a partial derivative, these are not the components, of a tensor. Of course, these are, again, the components of tensor. And this is just the components of a vector. And I told you last time, I wrote down the explicit transformation rules for the gamma symbols. This was quite some work. Maybe you remember that. I did a long calculation, but we found that they do not transform as tensor. And actually, I should probably very briefly remind you of these rules. I don't want to write them down again, but I think I had them somewhere last time. Yes, this was the transformation rule here. So you see it. The first term we had in the transformation rule was really that of a tensor, because for a tensor, you have for each upstairs index, you have a transformation of this type. That's something we looked at, and of course one has to sit down and examine it precisely to match all the indices. And for each lowercase index, we have a term like this. So we have two terms like this. So this would really be, if these were the components of a tensor, this would be the correct transformation. But we have this additional thing that depends on second derivatives and so on. And so I told you, and you should really remember the gamma symbols do not transform as a tensor. So, but now you see the relevance of them in this equality, because the partial derivative is also not a tensor. So if you take a partial derivative, you get a highly coordinate dependent thing. So if you again would translate this back into the manifold, you would get some, so let's suppose you take a vector in the manifold, go to a chart, take the partial derivative and write the partial derivative again in the manifold as a vector. Then this procedure would give you a different answer. You would get a different final vector on the manifold depending on via which chart you went. So this already shows you this cannot be a fundamental object, because fundamental objects should be chart independent. On the other hand, these gammas are also not, but the combination of them are again. So the left-hand side is something that is chart independent, because they are the components of a vector. And so we found essentially the way we can separate it into things that are kind of easy to deal with in a chart, namely the partial derivatives, which would be the wrong thing, but we saw the correction here. And of course, it makes sense that if two terms are individually not, or if two terms are individually chart dependent, it can still be that the sum of them is not. So the chart dependency of that is somehow compensated by the chart dependency of that. And the whole thing is again a nice, well-defined physical object if you like. So that's something you should keep in mind when you see such expressions here and here. What are the components of tensors and which are not? So it's, however, a bit a pity that these gamma symbols are not tensors, because this tells us, or maybe I should first say, or remind you that when I said how do we get, when I explained how do we get these gamma symbols, we really did a physics experiment. I always talk about this gyroscope, and maybe I should at this point also briefly explain one thing I mentioned about the gyroscope. So the gyroscope is a device which is essentially like a spin that rotates very fast, that just keeps its direction. So, and I really took this as a definition of keeping the direction. Now I think I swapped a bit in the examples between examples in space-time and examples in, for example, on the sphere where we only have space. And so there was a question about how would you actually do that on the Earth surface? Because if I really take a gyroscope and walk from here to Africa, then somehow the gyroscope, if it initially pointed horizontally, would, as I arrive in wherever in South Africa, probably point almost, or certainly almost upstairs, maybe a bit even behind me, so it would no longer be in that plane. However, when we look at surfaces of the Earth, then we usually in the differential geometric picture just want to look at them as two-dimensional manifolds. So we are not interested in this component orthogonal to the Earth surface. So this gyroscope example, you should rather understand as I would walk with my gyroscope, and whenever it pointed a bit upwards, I would project it down onto the horizontal plane. So I just make a projection, and I have, of course, means to do that. Another way you could think of it is, it's just, I mean, you can take any other, let's say, method that keeps things in the same direction. So one possibility would be that if you, for example, just drive straight there, and you always make sure your wheels are really straight, then you also have a guarantee in this case that you don't move. But of course, your car will not point upward, so this automatically somehow projects you down. But you need to do some experiment that corresponds to keep the direction. Of course, if you now ask me what is really the structure that goes into the fact that driving keeps you straight, then actually this has to do with the metric, because you have two wheels and the two wheels kind of go equally fast, and that defines what straight means. And of course, in space-time, we don't have a street where we have a reference. So in space, or in free space, and when we talk about curvature of space-time, this is really the curvature of, when you think of this whole thing being pictorially embedded into something larger. So I don't need to do this projection, but I don't also have a reference. So there the gyroscope is very appropriate. So the summary of that discussion is just, it's valid to think of the gyroscope. That's, I think, a very good example. But if you just move on the Earth's surface, you should always project it back onto the horizontal plane to make the examples work. Okay. Now, still, it's a pity that this thing is now basis dependent, because this somehow encodes the whole structure of the geometry. So if we do this experiment, so in principle, and maybe this was in a way almost like that, if people want to find out how curved is actually the Earth, if we didn't know it, and we would just start to do these experiments, we would start to walk around on the Earth's surface and compare arrows and see the differences that we get by walking along different paths to the same point. So we would want to kind of get the curvature of Earth, and we would do this experiment that someone takes a gyroscope, walks as last time towards the south and then towards east, and another one would first go towards east and then to the south, and then they would compare how the arrows differ. From that, they could in principle reconstruct the curvature of the Earth, and we will actually see how this works in general. You may even then do the calculation for Earth if you want. So this means these gamma symbols, encode a lot of the geometric information about the Earth. And geometric information is, of course, something that is not depending on the coordinate system. So you would hope that geometric information is something very general that is valid independent before I even choose a chart. And so we would really like to extract from these coefficients, which are chart dependent, some information about the curvature of the Earth that doesn't depend on a chart. Now, mathematically speaking, what we want is tensorial information. So we want to define tensors out of that object. And these tensors are then really things that live again in the world without coordinate systems. So they're well-defined physical things. And that's essentially the next thing we want to do. So the next chapters, and because we're almost at the end of the lecture, I will just give you essentially first an overview, or I will kind of summarize a bit two things. So we will have two chapters that follow. One will be called torsion and the other will be called curvature. And you should really now think of them exactly in the way I motivated it now, namely that these are notions, both the torsion and the curvature are notions that extract the relevant geometric information from this object and put it in the form of a tensor so that it's basis independent. So let me immediately define these things. The torsion is defined in the following way. So the torsion is a tensor, as I said. These are tensorial objects, and this is now a more complicated tensor. It's actually a 1-2 tensor. And the 1-2 tensor takes, of course, now one covector as an argument and two vectors as an argument, or vector fields, if you like, or it has to take vector fields. And what it does, it applies the covector to a vector, namely to the following vector, the vector that you obtain by taking the covariant derivative of the vector field y minus the opposite. And then you also subtract from this the Lie bracket. Okay, this sounds now quite complicated, but we will verify next time, and it's actually very easy to verify that this is indeed a well-defined tensor. Let me also immediately write down the definition of curvature. And of course, I mean, you probably know that curvature will be a very important object. So we are now finally there where we can write down the object that appears on one side of the Einstein field equations. And this will be essentially an object directly derived from curvature. So it's essentially a trace of this object that I write down. Okay, that's another definition. So see, we have now already enough structure to talk about the curvature of a manifold. And of course, the manifold will be space-time. So this is now the definition of curvature of space-time in that sense. But it's, of course, a general definition. So it's called the Riemann curvature. And the Riemann curvature is also a tensor. It's a 1-3 tensor. And the 1-3 tensor is, of course, now even more complicated. I call it R. It takes a covector and three vectors. And the first, by convention, is called Z. Okay, this is just a convention that I'm using that is sometimes used. And what does it do? It applies the covector to a vector, which is obtained by first taking the derivative in x direction, then the derivative in the y direction of the vector field Z, then the opposite order of the derivatives, again applied to the same vector field Z, minus the derivative into the direction of the Lie bracket of x and y of the vector field Z. So it's an even more complicated object. And don't worry at the moment that it looks complicated. We will actually understand what it means, and it has a very good, nice, intuitive or geometrical meaning, I should say. And once I explain this meaning, which I will do next time, you will see why this definition actually makes sense and why also these Lie brackets are there and so on. Okay, but that's essentially where I wanted to arrive at today. I just now want to, how this now answers the question of before. So I said before we want to extract the geometric information from the gamma symbols. Of course, the gamma symbols are the ones that are kind of encoded in this derivative. As you can just see that here, this y is not very visible, so this should really be a y. So these encode the gamma symbols. So this is the parallel transport is encoded in this covariant derivative that we defined. And now we define a new tensor, this tensor here. And this tensor obviously depends on indirectly, or rather directly actually, on these gamma symbols. We will write down an explicit coordinate expression, and there we will explicitly see how the gamma symbols enter. Essentially what we will see is that the torsion is just the symmetric, the antisymmetric part of the gamma symbol, whereas the rotation is a slightly, the curvature is a slightly more involved expression involving derivatives and products of gamma symbols. So these are new objects which in coordinates are functions of the gamma symbols, but they are coordinates that correspond then, of course, to the coordinates or to the components of a tensor, and therefore they are at the end coordinate independent objects. And these objects are really the geometrically well-defined objects that tell us what how space-time looks like. And there will be an axiom. The axiom will be that in space-time the torsion is just zero. And there will be the Einstein field equations, and the Einstein field equations will tell you essentially that the trace of this, more or less, I mean, there's some expression derived from this, is directly proportional to the matter density that you have at the space-time point. So the fact that this is zero together with the Einstein field equation, that will determine that, more or less, we have the whole geometry of space-time. So in other words, these are the objects via which we define the geometry of space-time. Okay, there will still be, of course, a few other things we have to learn to really phrase that precisely. We also have to talk about the metric. That will be things I will do next week. Okay, but that was all for today. You should also, with these notions, be able to do the exercises. Again, I encourage you to do them. It's really useful to do them. I think it will be much easier to follow the course and understand what I'm telling you if you do the exercises. So please use this opportunity. Okay, then see you next week again.